Alright, let's continue with this osdev here. I'm going to try and go over interrupts today, if I have time, as much as I can, for setting up basic software, hardware interrupts, exceptions, the PIC, the programmable interrupt controller for hardware interrupts, setting up the IDT and ISRs for exceptions and software interrupts, and then maybe a syscall. Just a basic example for that, set up a syscall handler and have a sample one. But I have, tabs opened up here, osdev, just the interrupts tutorial. I'm not going to follow exactly what they have as far as code and stuff, but I mean, the general flow will kind of be similar here. So to use interrupts, in my OS, it's a 32-bit protected mode operating system right now. So to use interrupts, which we don't have anymore since we switched from real mode to protected mode, we have to set up an interrupt descriptor table. So in real mode, in 16-bit, it had its own version of an interrupt descriptor table in the form of the interrupt vector table, or IVT, which is at the start of memory and contained basically function addresses that were called when interrupts were fired. So interrupt.h for video services or what have you. For the BIOS, just went to basically a 10h offset from the start of memory, aligned however it was, and then loaded whatever function was at that address at that offset, and then went to that sort of interrupt handler. So we kind of have something similar here for protected mode in the form of the interrupt descriptor table, which is basically an array of structs, pretty much, an array of data structures, which define descriptor table entries inside of this descriptor table. But what these really are is just the addresses of functions, and those functions are called ISRs, or interrupt service routines. They are routines that service an interrupt. So you basically have a big array of this type of structure here, interrupt descriptor table entry for 32 or 64-bit. I'll be doing the 32-bit because my OS is still 32-bit, but it gives the low and high address of the function that you're going to set. It gives the code segment that it runs in, and then a reserve thing, and then it has some flags determining if it's a trap gate or an interrupt gate or stuff. We're basically just going to set up a big array of these entries and then set functions. The addresses of functions we're going to set within the entries within this overall table, so that when an interrupt is fired, it'll look at the entry in the table and say, okay, I need to go to this function to execute this interrupt. The basic purpose of interrupts that they said was, you don't want to poll everything all the time. So like right now, when I get a key from the keyboard, I have to pull the data port for the keyboard and say, okay, are you ready to send data? Are you not ready? If you are, is there any data on the bus that I can get? If there is data, I want to get whatever that key was pressed, right? You don't want to be polling the whole time. That's kind of wasteful. You can just have like the keyboard send you an interrupt when it's ready or when a key was pressed, instead of not knowing when it was pressed and having to poll the system for all that. That's kind of the purpose of interrupts. But yeah, that's enough little spiel here. I'll get to programming stuff, I guess. I have enough files to where it goes off the screen when I do a basic tree command now, so that's fun. But I'm going to make yet another folder here inside the include folder. It's going to be for interrupts. Maybe I don't need to separate it out as much as I am, but that's okay. I'm probably going to have 4 separate files here. I'm going to have a file for the interrupt descriptor table and its functions to set up basically interrupts there. I'll have one for, I guess, exceptions by themselves. I'm not sure I have to split that off, but I can just keep it separate to make things a little easier conceptually. So the interrupt descriptor table, I have one for exceptions, and exceptions are pretty much the first 32 interrupts within the interrupt descriptor table, and they're kind of Intel mandated for x86. You should have these 32. They're for exceptions, which are kind of stuff for like hardware faults or division by zero or page faults and other things. I'll have one for the PIC, the programmable interrupt controller, the PIC, although nowadays there's the advanced programmable interrupt controller, or APIC, or even io.h, which is, I guess, input-output programmable or maybe memory mapped APIC or something. I'm not too familiar with that, so I'm just going with the really basic one here. And then I'll have one for syscalls, which are a software interrupt. I mean, you can set multiple, but if we take like the Linux example has interrupt 80 in hex or 128. So 0x80 is their kind of syscall software interrupt. So if you call int 0x80, it'll call basically the 128th descriptor within the interrupt descriptor table, and that'll be your syscall handler. So it'll check whatever you have in EAX or however you want to differentiate what syscall you did, and it'll go and do, malloc or memory map or open a file or something, whatever you have it defined as. But I'm going to have those 4 files that we can get to. So the idt.h here will be basic data types or structs and functions to set up the interrupt descriptor table. I'll have some basic sort of empty ISRs to handle exceptions and software interrupts in here, and then functions to set up the IDT itself, which we'll use in the kernel to install interrupts in a bit. So I'm going to have types similar to what the osdev wiki page had. I'm going to have a struct to hold the interrupt descriptor table entry, or, well, the entries, yeah, that'll be in an array, which will be the interrupt descriptor table. So I'm going to make sure it's exactly how big I specify with the packed attribute, and I'm going to call it, I'll do this, IDT entry 32. It's a 32-bit descriptor table entry, we'll say. Each one of these describes an interrupt service routine, or ISR, which is just a function. So each one of these is going to describe where in memory that function lies to service the interrupt. And that's split up inside of this entry between the low and the high 16 bits for a 32-bit address for this 32-bit IDT entry. So we'll have ISR address low, which will be 16 bits, and later on we'll have ISR address high for the higher 32 bits. So we have the low and high parts of the address. We also have after here the code segments. I'm just going to use the kernel code segments. We'll call it kernel CS. We need 1 byte reserved for some reason. I don't know if Intel states why it's reserved. They just say it's reserved, so that's fine. We'll just do set to 0 reserved by Intel or whatever. Then we'll have another byte for attributes or flags. I'll call it attributes. So this will be for type and attributes, the type of interrupt service routine we're describing in this entry. You can also call it flags, I guess, for that. And that is it, actually. So the interrupt descriptor table, to load it with the instruction for the CPU to use it, it's similar to the global descriptor table in that it has a specific register. So you have a GDTR, global descriptor table register. It's the same thing for this. There's an IDTR to load it to the interrupt descriptor table register. So just to make it a little bit easier, I'll have a type def for that as well. I'm going to call it IDTR32. Well, these are type defs too, so let's put I guess we'll put T's on the end. This is going to have a 2-byte base and a 4-byte limit. Or wait, no, I got that backwards. 2-byte limit and a 4-byte base. So the base address and then wherever the end of the table is, or I guess the size, if you will be the limit. Let's put a couple comments here. So to actually make the interrupt descriptor table, as I said, it's basically going to be an array of these structures. So we'll make one of those. So IDT entry 32T, I'll call it IDT 32. And I think the limit is 256 separate ones, 0 to 255 IDT entries. So I'm just going to make it the max, the limit here. This is the actual IDT. It's just an array of these structs. If we want to actually use the register here, we can set that up as well. Descriptor table register. So there are a few different types of interrupts. There's software and hardware interrupts. There's exceptions, which are sort of in between. Well, not really in between, but I'm going to set up a couple sort of interrupt handler functions for these. But there are specific exceptions that have error codes and ones that don't. In the Intel manual here, what volume is this? Volume 3, chapter 6, section 6.3. Sources of interrupts here. There's external or hardware generated interrupts. There's software generated using like the INT assembly instruction. For external interrupts here, hardware generated, including exceptions. Exceptions are the first 32, so vector 0 to 31. 32 to 255 are free. We'll define those for software interrupts or remap the pic to those. But for these exceptions, some of them come with error codes and some do not. But we're going to set up default exception handlers for all of these. So I'll have one that handles a general exception, one that handles an exception with an error code. These, and then, software interrupts will be a little bit different. And the way we handle that is some stuff is pushed onto the stack for these exceptions, which I think was in 6.12. Just go down here a little bit. So for interrupt and exception handling, and depending on the flags that you do, which are that attribute byte within the IDT entries, will kind of determine what kind of interrupt it'll be when the CPU calls it, but it'll put certain stuff on the stack here. So specifically, for interrupts and for exceptions, they'll have an error code. This stuff is going to be pushed onto the stack. So I'm going to have a sort of interrupt frame, so to say, that sets this up. So I'll have a struct that has these values that we can pass to our function, to our interrupt handler. So it'll be sort of easy to use within C. It'll be a struct parameter that includes these things, is why I'm showing this here. It might be small, so that's probably too big. That might be easier to see, but it'll push the flags register, the code segment, the instruction pointer, so it knows where this is at. It knows where this was called from to go back to execute after the interrupt's handled. And for exceptions, it'll push an error code onto the stack. And depending what privilege level it was called from, which I'm not really messing with, but I think for interrupts, I'm just going to assume a user privilege level, so level 3. The kernel's a level 0, so it'll push the stack segment and pointer in addition to these things, and then an error code as well if it's an exception that needs one. So just showing this because I'm going to have a struct that includes these values, so you're not confused. Because as of, according to Clang and GCC, and GCC doesn't specify the interrupt frame, but you can make a function with an attribute interrupt that takes one of these interrupt frames, and this frame structure here is sort of defined to have these values in it. That's why I'm showing this. And these will all be, I'm in 32-bit, so these will all be 32-bit values. They'll all be double words. Because, I don't know if this says it or not, but when these things are called, I guess this doesn't really say it right here. When these things are called, I think the code segment is padded out to 2 bytes. So you don't have to worry about alignment. These are all going to be double words. So I'm going to set that up here. Just put that. We'll call it an interrupt frame, I guess. Int frame 32, something like that. I guess we're using it as a parameter. We don't need to put the T on, but whatever. I'll put a T on there. So I'm going to have instruction pointer. So we'll have EIP. Then we'll have CS. So I'm going to lay this out sort of upside down from how they lay it out here. In memory, we're going to start it here and then go here, 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 and here. So I'm going to lay it out like bottom to top instead of top to bottom, how it's pushed onto the stack. So, and the reason I'm doing it is so if you have a C function here, you're accessing the frame from the struct that's passed. If you go to the start of memory where the struct is at, you'll have this value first. If we define it first in the struct, it's laid out that way in memory, right? So if we define this first in the struct, then this will be first. If we access it in memory, it'll be first as it's passed to the function. Then this afterwards, and then this afterwards, and this afterwards. So if you handled this like in assembly or something, you could do SP plus, whatever this would be, 4, 8, 12, 16, 20, something like that, depending how it's laid out. This way we can access it as struct values and it'll still be, it'll work. It'll be kind of equivalent. It's not a great way to say that, but it's kind of how this will work. But these will all be double words. I'll have the flags pushed, then we had stack pointer. For these, I'll have the stack pointer and stack segment. So this will be sort of interrupt frame to pass to, I guess, interrupt handlers. I'll call them ISRs. Okay, and then I'll have a couple functions to handle these things before I set up the IDT. I'm going to have a default exception handler, no error code, and I'll also have one that includes an error code. So for these and Clang and GCC, we can have an attribute, a function attribute for an interrupt, which is very handy. Although there's a few different ways of doing interrupt handlers. You could have a naked attribute function, which doesn't have a prologue or epilogue, and you have to just use inline assembly and you can set it up and do it yourself. That's fine too. Or you could write these in assembly and call out the C. I'm going to use the functions with the interrupt attribute here. And what that'll do, the interrupt attribute will cause it to use an iReturn instead of a return instruction to return from this, so you don't have to specify iret, because normally you need an iReturn instruction for an interrupt return at the end of your interrupt service routine. Although I'm in 32-bit, so it would be iret_d or maybe iret_q if you're in 64-bit, depending on the assembler you use. It'll use iret instead of ret to return. Everything except for e flags is restored by iret. If it needs an error code passed, then you add that as another, it says uword. This is basically a double word, the 32-bit value here, if you're in 32-bit. But you pass that as the second parm in addition to the frame. So that'll be my interrupt handler for error codes will look like this. Which I thought was kind of weird, because in C, usually how it works is these are popped off right to left. So this would be on the stack first and then this. But according to how Clang and GCC handle it, the compiler will arrange to pop the error code off before the iReturn instruction that pops the other stuff. So even though it's this way on the stack, and normally how that would work is this would be on the stack first and then these. Well, I mean, that's how it works, but this will be popped off and then iReturn will pop this stuff off. So it'll work fine. It just looks kind of weird. At least if you're new to it, which I am. But anyway, the exception handlers here, I'm going to have be void. They're not really going to return, so they're not going to return a value. Well, there's a possibility that they won't return. I'll call this default exception handler. And this is going to take in one of these frames, iframe32t. I'm going to have a pointer to this. Call it intFrame32. Call it intFrame32. And for the one with an error code, we'll also pass in an error code. So that should be okay. Okay, so for these basic ones, all I'm going to do is put a message on the screen. I'm not really going to handle these because we can make specific exception handlers later, which is why I have a separate header file for those. So these are just going to be defaults set up when the interrupt descriptor table is set up to handle anything that we haven't explicitly set a function for, right? We're not handling the exceptions. We want something to happen so everything doesn't crash if one of them has happened to be called. What I'm going to do is just put a message on the screen, pretty much. We'll just do this, x equals 0, y equals 0. I'm just going to print a string because we'll have that included, but I think I am going to include, if it needs it, header files that need other header files. So just in case I want to mix and match where they are, I don't need to put them in specified order. It should include, all these are going to have if define, define, not define, whatever, header guards because of these pragma onces. So I think this is okay, but if I start doing this everywhere, I'm hoping it doesn't slow down compilation a whole lot. If it does, I'll mess with it later. But okay, I have an error code include with this. I'm just going to print strings out. So print it on the screen. We'll have a message like, I guess just default exception handler. I'll put it all in caps. So I know it's coming from something that I didn't really set up. I'll put no error code so we know that's true. And we'll do that. So it'll be on the top of the screen here. I guess I don't need that. It's not really going to go down and print anything else, so I don't need the new line. And that will be it. That's really all we're going to do here is just print a message, but we're going to put it within the interrupt descriptor table so that if an exception is called, it'll call this, or it'll call one with an error code. I'll do this here. We'll put this with an error code. It could be in hex or in decimal. I guess we'll do in hex. They're probably defined as hex. The error code will be whatever the error code is. So we'll just do that. Some of my functions have good interfaces. Others don't, but that's okay. Okay, so those will be the exception handlers. If we just want a regular interrupt handler, like for software interrupts here, we can set those up as well. Instead of an exception, we'll just call this an interrupt handler. And it'll be similar to these, except I will call it, I guess, default int handler. And it'll just take the interrupt frame again. But I'm just going to print string here. It'll be default int handler. It would be nice if I passed like the interrupt number that this was at. I guess maybe I could calculate that somehow, but that's beyond the scope of what I want to do today. So I'm not going to do that. Just going to call it the interrupt handler. So we know it's not an exception, which are the first 32 interrupts. It's one of the other interrupts. I'll have a function to add an interrupt service routine to the interrupt descriptor table. And then I'll have a function later to set up the interrupt descriptor table. I'm going to call this set descriptor 32 or something. That's fine. Set idt descriptor 32. That's fine. We'll call it that. This is going to take in what number we want to do. So entry number. The IDT entry that we're going to be setting here, whether it's interrupt 10 or 80 or something. And we're going to take in the address of our function that we want to handle that interrupt. So we call it a void pointer to the ISR itself, which is just the address of a function, which is sort of like a label. If you had code under a label in assembly, that label's technically a function if you use the call instruction on it or what have you. So same principle here. You can refer to functions like default int handler. If you refer to this name itself, it'll be an address in memory somewhere where that code is at. So if we pass that address to this function, then we can add it to the interrupt descriptor table, since it will just be, sort of splitting that address up and specifying what code segment it's at in memory. Okay, and other than that, we need to set the flags, whether it's flag, trap or int flags or something. So I'll just have a flags byte here. And this will be similar to how osdev had it set up. So interrupt descriptor table. I know I'm not specifying the flags, sort of the bits that are going to be set within these. Type attribute here, p_dpl_s in the gate type. So that is this byte that I had called attributes, split up between these. The present will be 0 if you're not using it, 1 if you're using it. DPL, the privilege level. For a regular interrupt, I'll probably just make the privilege level like 3 for user mode. That's fine. Storage segment will be set to 0. The gate type is what we're going to be changing mainly. And I'm going to be using, I think, an interrupt gate and a trap gate for 32 bits. Not going to be messing with tasks just yet for the task segment register or anything. But I'll have, for the regular interrupts, we'll have an interrupt gate. For the exceptions, we'll have a trap gate. So I'm going to have constants for the trap and gate flags that I'm going to do. The trap gate I'm going to use for the exceptions. When an exception occurs, that should correspond to a trap gate. So I'm going to use that for exceptions. The interrupt gate will be interrupt service routines, the regular ones like doing the int instruction. That's why there's a difference in how those are handled. So here we go, yeah. So they have an example, 8e for an interrupt gate. The privilege level is for the kernel, it is present. Storage is 0 because it needs to be for an interrupt or trap gate. The type is 111, which is 8e. So 111 means it's the interrupt gate for 32-bit. The trap gate would be 8f, just because that bit has to change there between interrupt and trap gate. Task gate I am not going to use, but anyway. So I'm going to put those up here actually first. So we're going to have a trap gate. These will be flags. I'll call it trap gate flags. This will be 8f. And I'll just set it out as the OS Dev Wiki had it set. DPL is 0, S equals 0, type equals 1111, which defines a 32-bit trap gate. All right, then we'll have interrupt gate flags, which will be 8E. The only thing that changes here is going to be the type from 4 ones to 1110, which is a 32-bit interrupt gate. And then if I want another one for later on for system calls, it can be called from, user mode code or whatever. It'll be called at runtime from some other program that's been running for that the kernel set off. I'm going to have the interrupt gate, but it's going to be used from a different privilege level. So I'm just going to call it, I guess, int gate flags user or interrupt gate user flags, or I'll just end these all in flags to be consistent. But the difference here is that the privilege level will be set to 11, and that is EE. It's 14 and 14, 1110, 1110 in binary for that byte. So 32-bit interrupt gate called from privilege level 3, pretty much. And I'll be using that for syscalls specifically. That's why I have that set up differently. But okay, we have those defined. We'll have a thing to set up the IDT. Guess I'll set up this first, add the ISR to the IDT. But okay, so how am I going to add the entry to the descriptor table? Forget what I called this, IDT 32 entry T. So I'm going to set up one of these. I'll copy a word there. And it's going to be a descriptor. So one of these is going to be defining what descriptor we're adding. So this will be a new descriptor. So I'm just setting that up here. And that pointer to the descriptor, I guess I can have this up here to make more sense. So I'm going to have a pointer to one of these. I lost it here. Put within this array, which is our actual table. So a pointer to one of these, I'm going to put the data at that pointer into the array at whatever entry number was passed, if that makes sense. And then this void pointer is going to be the address, for this function that we're putting into this entry, into this table. So to get the right element in this overall array of the table, I'm going to take the address of that entry number. So if we have 256 entries in this array, and each entry is one of these, if we want to set interrupt 10, then that would be the offset for the 10th entry. I think this works. We'll find out. But we're getting the address of that specific element in the array. So it looks a little jank, but get the address of this array element. And then to set the data at that address, at this array element, we're going to fill out the values within this entry struct. So descriptor address low, ISR address low is going to be whatever pointer we passed into this will be a function name. But it'll just be an address. For me, this is going to be a 32-bit descriptor, so I'm going to cast the address to 32 bits first to cut off any other things that may be there. But I'll cast it to 32, and I'm going to AND it with, the lower Fs. So this will be the lower 16 bits that we're just kind of grabbing here. This will be low 16 bits of ISR address. Obviously, I don't need to write that out, but I'll write it out anyway. This has 1, 2, 3, 4, 5, yes. Except this will be the kernel CS. This will be reserved. This will be the attributes byte. And this will be the high address. So I can get that off the screen here. Okay, so the kernel code segment, to be really easy for this, I'm not going to deal with different code segments here, and so I just called it kernel. I'm only having one code segment that I'm going to use for this. And I will use the one that was set up initially in the bootloader, which I think is just 8, right? Wherever I set the GDT down here somewhere. Yeah, I offset 8 for the code segment, so this is just going to be an 8. So this whole thing, I'm just going to set to 8. That is the code segment that is being used for the kernel, so that's what I'm going to set here. And the the reason it needs to know what code segment this code is in is, you know, so you know where it's at in memory, where the executable code is at. Reserved has to be set to 0, so we can just set that to 0. Must be set to 0, or so they say, but I'll do it to be safe. Okay, the attributes are basically going to be this flags byte that I passed in, just to be easy. I think that's how Dev Wiki had it. Just set this equal to the flags. Type and attributes. Whether it's an int gate or trap gate or what have you. You know, what privilege level it's being called from, that's included within these constants here. So that flags byte is going to be one of these, depending if it's an exception or an interrupt or a syscall or whatever that I'm trying to set up here. Then the address high is just going to be the upper 16 bits. So what I'm going to do is take 32-bit here, I'm going to shift that over by 16, and that should be all we need to do, actually. I don't think I have to and that with the Fs. Although I guess if you want to be safe, we could surround that with parentheses and it with this. But maybe I'll do that anyway. I don't think I did that. No, I didn't do that before, but I'll do that here to see. I don't think that'll break anything, but we'll just be explicit. We're getting 16 bits here. CS reserved and attributes. Yeah, so that's all we need. Okay, so now that we have default handlers for exceptions and interrupts, we have our table defined, our register defined that we're going to move the table into, and we have a way to add descriptors to the table. I can have a function to set up the interrupt descriptor table itself, you know, using those other things that were just defined. Set up, I'll call it initialize as well. Set up or initialize the IDT. Init idt.32. I guess that's fine. We'll initialize it. It's not going to take anything. It's not going to return anything. So what we're going to do here is set the values for the interrupt descriptor table register. So this iddtr32. And it has a limit and a base. So the limit was defined as 2 bytes, 16 bits. And the limit, how big the table is, in other words, the size of the table, the size of this array of 256 entries is going to be 256 times however big this is, which is, I don't have a sizeof operator yet. I don't think I can use sizeof without the standard library and everything, so that's okay, because these are 2 bytes, 2 bytes, that's 4 bytes, 5, 6, 7, 8. Since it's packed, this will take up exactly 8 bytes, or 64 bits. So we can do 8 times 255. I think should be fine. Well, no, there are 256, yeah. And there are 256 descriptors. 0 to 255, yeah. So I think it will be 256. Okay, and then the base, wherever this starts at in memory, is going to be wherever this table is located at in memory. This is the table itself, so wherever this is at is where the base is at, because the base plus the size of the table is, you know, what the table is, right, in memory. So this is 32-bit. Is going to be the address of the table, or I guess the first part of the table. This is how Dev Wiki had it set. So I defined it this way because that's how they had it, right? It's just IDT32, okay. So I don't need that underscore. So I don't know if I could just point to IDT32, but I guess that would be, that's defined as an array with 256 elements. So I guess that's why that wouldn't work, but I don't see why the address of that wouldn't work. But I guess I have to do this because each entry is this many bytes, and it's sort of a pointer to the first entry in the table is how this works, I guess. But okay, so the first entry in the table is where the table starts. So the address of that entry is where the base is that we're going to load to the interrupt descriptor table register. That's fine, that makes sense. Later we'll have an instruction for that. after we set up the entries. But the instruction is going to be the assembly instruction, load interrupt descriptor table. So it'll load the register with the value where the table is. I'll load it to 0. I think this is how the Dev Wiki had it set up. So no, it's not going to output anything, but as input, we're going to give a memory address where the table is at. And that is going to be our idt.r32 that we just set up. So wherever this is at in memory, it's going to be loaded into the interrupt descriptor table register with this instruction. Okay. But that will be last. I'm getting ahead of myself here. Okay, so let's set up the exception handlers first. ISR 0 to 31, the 32 exceptions. So for each entry number here, 0 to 32, well, 0 to 31, sorry. So if it's less than 32, needs to be semicolon, we'll do plus plus. Some of these will take an error code and some will not take an error code. Yeah, default exception, I named these the same thing. This needs to be error code, I'll do that. Default exception handler error code, and then default exception handler without the error code. And those again, so I don't forget, are defined in the Intel manual. I think it was 6.3 in this table here, 6.1, protect no exceptions and interrupts. So if the entry number from 0 to 31, if the entry number is 8, 10, 11, 12, 13, 14, 17 or 21, then it will take an error code. If it is not one of those, it will use the exception handler for not using an error code. So I'll just have a really basic way of doing it here. Just a bunch of conditions here, which is not the best way to do this, but whatever. We can be explicit, it's fine. So if it's 8 or 10, or you can't type, it's 11 or 12 or 13 or 14. Put it down here, 13 or 14 or 17 or 21. Then we want to give an error code. Exception takes an error code. Else exception does not take an error code. Line that up. Okay, so the error code, how are we going to add these to the IDT? Well, we have a function for doing that now, set the descriptor, so we're going to call that. We're going to call set IDT descriptor 32. The entry number is this entry number we're setting here. So it'll be 0 to 31. We'll give it the entry number, we'll give it a pointer to the function that we're going to pass, which will be, if it needs an error code, it'll be this function here. Default exception handler error code. And if you just pass this as the name, that'll be an address. So it'll take that address as the void pointer here, and it'll be all right. And then what flags are we going to do for this exception that takes an error code? We're going to give it the trap gate flags, because you need the trap gate for any getting ahead of myself. 32-bit trap gate needs these flags, so I'm going to pass this value here, trap gate flags. That's what I want to say. I'm trying to talk too much. I wanted it to go there, it's okay. Okay, yeah, trap gate flags, and that is all we have to do here. We're just calling this function to set the descriptor within the overall descriptor table here. So the only difference for the regular ones that don't take an error code is we're going to use the other function to handle it. So call it with the regular one. And then after we set the exceptions, I'm going to do a similar thing to set up all the other interrupts. And these will be ISRs 32 to 255. We don't need to set this up again because this needs to be 0. There we go. You know, after this loop completes, if we made this parm outside of here, then entry would be 32 after this is done, but whatever. I made it 2 separate loops, so maybe that's not as efficient. It doesn't matter. So this will be 32 and it'll go until 255. Actually less than 256, but since this is 8-bit, that will always be true. It'll never end, so we'll do 16. That'll work. Otherwise it would wrap around and be wrong. Yeah, so that's okay. So we'll call set interrupt descriptor. Except instead of the exception handler, I'm going to use the default interrupt handler. So the default int handler. Oh, I didn't copy that how I want. That's okay. Default int handler, and instead of trap gate flags, we're going to use the int gate flags. Yeah, these regular ones here. And later when we set up syscalls, I'll use the user flags, but we can set everything by default to take the default handler, and then any specific interrupt handlers we want to set up, we can do in the kernel and use, user gate flags and set up different functions that we want to set for handling those interrupts. But this is just a basic, bare bones. This will be setting up the interrupt descriptor table. Just with default functions here. So that'll be okay. That is all I had in this file, so that's good. Okay, I'm going to go ahead and add that to the kernel and then compile to see if everything breaks or not, right? I'll do that. So this will include interrupts idt, and we can try calling it here. I guess I'll do it after here. Set up interrupts. Kind of want to make this more delineated and better laid out anyway, but whatever. This is still all before the user input. It's all part of kernel setup. So setting up interrupts. So that will be calling that function down here, init idt32. Doesn't take anything. And we'll see if everything works or not. I am not setting the interrupt flag. That's what I wanted to get to. The Dev Wiki had that. Just remembered. The Dev Wiki had that at the end of, I guess at the end of this. Yeah. So when they set up the interrupt descriptor table, they were setting the interrupt flag with STI. I am not going to do that because what that will do is enable hardware interrupts, or as Felix Cloudier said it better, not always. Setting it, the interrupt flag being set within the flags register, or eFlags, since I'm in 32-bit, allows the processor to respond to maskable hardware interrupts. So when setting up the pic, I can kind of mask everything off or on to enable or disable hardware interrupts. That won't affect non-maskable ones, which I haven't researched too much, so I won't go into that. And it does not prohibit exceptions. So anything that generates an exception or a non-maskable interrupt will still be set off. But for other hardware interrupts, programmable interrupt controller or otherwise, those will still be enabled if STI is on. So I'm going to keep it off until I set up hardware interrupts, so we don't have anything, real crazy going on, breaking stuff before I'm ready. So I'm not setting STI on yet. Sometime after setting up hardware interrupts. Turn on, set if. Let's do this. To enable non-exception and not NMI interrupts. Okay. So this will be later when I'm sure everything works, hopefully. So that'll just be STI. But we'll do that later. Okay, let's see if this works. It won't do anything, but I think setting all that up in memory will make the kernel bigger, and if it doesn't, it'll break at runtime. So include print types not found. Yes. Because that's up here, right? Or maybe I don't have to do include because that's already in the include file. It's in interrupts. Okay. Right, maybe I just need to do, one folder up. Yeah, that was it. Okay. So I don't think this will work because setting the interrupt descriptor table up takes up a lot more memory in the kernel. Yeah, the kernel's now 1E, and then 1D, 10. Okay. So kernel's 1E, which is 2 bigger, 2.9, 3.6, 5.3, C. Okay. But we can see if this works anyway. I'm hoping it does, but it might not. So I don't know. No, that looks good actually. Okay. Okay. That's okay. Can we load a program? Yes. Okay. I feel like I messed that up, or I messed this up when I was testing, is why I'm very cautious right now, but everything seems to be working so far, so I think I worry too much. Which is definitely true, but okay, it's working right now, so we're okay. So that's good. I set up the IDT file. We have an interrupt descriptor table set up, even if you don't believe me, because we're not using it yet. It is set up. So what I can do is set up hardware interrupts or system calls or the PIC exceptions. Let me set up, like, since we set up interrupts and exceptions, I will do a basic exception for divide by 0 and then test that out to see if that works. So I'll do that next. Okay, so I'm going to set up one basic exception here just as an example and to show that it works, hopefully. So I'm going to put that in the exceptions.h header here. So functions ISRs for exceptions, which are interrupts 0 to 31 in the IDT, but I don't know if I need to put that, it's fine. Okay, so exceptions. Interrupts IDT, because I'm going to be using the interrupt frame for these exception handlers here. And then I'll probably just print a message similar to the default exception handlers. So I'll also include the print types file just in case. Okay, so what this is going to look like is the exception handlers here. I'm going to make one for the divide by 0 error just because it's the first exception that's kind of defined. This one here, divide error. So div and idiv, if they're, well, not necessarily divide by 0, just a general divide error, but this affects div and idiv instructions, so we can do a divide by 0 and see if it calls this exception, right, from the calculator or somewhere. So that's what I'm going to be testing this with, but that's the first interrupt at vector 0. It does not include an error code, so we'll use the default exception handler. Sort of a prototype. And I'm going to call this divide by 0 handler. I guess that's fine. It'll take in this frame, which is why I'm including this IDT header here, because it needs that interrupt frame. And I'm just going to print a message at the top of the screen again. But actually what I could do is change the text to make it all scary red or something, so I guess I'll try that. So I think this is still 2dgraphics.h, right? Not interrupts. Yeah, 2dgraphics.h, okay. This will be, the user graphics info. I'm going to take the foreground color, which is going to be the text color, so I'm going to save that off because I'm going to change it. So save the current text color, and then we'll print a string out. And we'll change the color here. So color, for whatever video mode they're doing, I'm going to have it be red. About as red as it can be, just pure red here. And I'm going to print, do divide by 0 error. Exception handled. It'll print that at the top of the screen at position 0, 0 for the cursor. And then instead of breaking everything installing, we could go back to the kernel or have the program continue or what have you. For this basic example, I'm going to have the program continue on. So as part of the frame, the interrupt frame here, since we pushed all of this stuff on the stack, we know where the program that called this exception, in this case, is coming from. So we have the instruction pointer code segment, we have the flags and everything. So if we have the instruction pointer, in order to continue on, an easy way to do that is just to increment the instruction pointer here. Since it's in 32-bit, this pointer should increment by 4 bytes. Not 4 bytes, just the 32-bit value I'm going to increment to try to move past whatever happened here. This is not a great way of handling this. I'm not sure it'll even work in any general case. I'm also not exactly sure I need it, but I did this in my test, so I'm going to try it here. So I'm going to put a attempt to move on after the offending div or idiv instruction. We'll just call it that. We'll try to move on by incrementing the instruction pointer so that when we return to where this was called from, where it happened, then it will have moved past that instruction. It won't be trying to divide by 0. It'll move to whatever the next instruction was. So that's not a great way to handle it, but this is how I'm going to handle it. Print a message and move on, pretty much, by incrementing instruction pointer. We'll call it that. And believe it or not, that's all I'm going to do here for this exception handler. So I'm going to put that inside of the kernel. Exceptions. And I'll put that down here. I'll do this setup exception handlers. I'm putting this so I don't forget. Like, these are specifically just the first 32, because I know I'm liable to forget that. That's why I keep putting this here. Okay, but in the kernel, we can call that function we had to set the interrupt descriptors. We can call this within the kernel to set the descriptor for the first interrupt, interrupt 0. We can set that entry number again, even though we already set it down here to begin with. We can set a specific function there, which just replaces that entry within the array for the interrupt descriptor table. Okay, I forgot the name of it. I will do that. Set idt descriptor 32. It'll be entry number 0. The ISR we're going to do is that exception handler, so divide by 0 handler, and then we're going to give it the trap flags, which was called trap gate flags, because the exception needs those flags to be a valid exception in 32-bit. That is a function address, not a function itself. So, okay. Divide by 0, error. This will be ISR 0. And we can set up additional ones there, but I think that's what I called it, so. Div by 0 handler, yes, okay. So that should set that up as the first interrupt here, and then after this point, if we make in this case, a divide by 0 error, it should call that exception, it should print the message on the screen and move on. So I'm gonna try that out here. And it didn't work. That file was not found, okay. I'm not really sure what I need for this, so if I just do this, does it work? No, okay, do I need that? Print type's not found, yeah. Because that's what I have to do. Okay, so I do need this to go outside and then back in for some reason, that's okay. Frame EIP is not what it was called, what was it called? Sorry, it's EIP, but the frame passed to it is called int frame 32. That's what I wanted. So what I could just do is call it frame, and then that would work better. Let's do that. Call it frame, and then what I meant to do, since it's a pointer, was do an arrow. Increment that value, okay. And when the iReturn instruction, which here is implicit, because we're using attribute interrupt for this function, when the iret d, because we're 32-bit in this case, is executed, the interrupt frame, those contents will be popped back out, and the CPU will continue executing. So that's why if I increment the instruction pointer here, it works, because that new value is going to be popped back out when this interrupt returns. And the CPU will execute at that new point because we set the instruction pointer. That's why I think it should work. So, and that fixed the error, so that's good. I'm going to try that out here. Do 800 by 600 to have the screen be smaller, and it doesn't work. That's good. What if I don't do anything? And it's broken. Okay. So setting up the exception broke everything, as is tradition, as is wont to do. Let's just make sure that was the issue before I go and debug things. Actually, you know what it was, is I didn't reset the boot sector. So I'm not sure why it was working before anyway, because I forgot to do this. Oh wait, no. 1D. We'll be reading 1E sectors. That wasn't right to begin with anyway, but okay. 1E. Yes, starting at 2000. The kernel is 1E. Because when we make it, it's 1E. Okay. So was that? I didn't want to do that again. Cancel. Okay, that was the issue there. Okay. You got to set the new values when you set the new values, dummy. Otherwise it won't work. Okay, so we'll set that, we'll enable that. Divide by 0 handler. It's set up in the boot sector, so the right amount of sectors will be loaded to the right location. Now we'll make it smaller. So if we go to something like the calculator, you know, it works fine. So the divide by 0 will be handled whenever we divide 0. So there we go. So divide by 0 error exception was handled, and then it moved on because the cursor moved back here. And in the calculator, it just took the first 10 that was put in. I guess when it divided, it moved on, it didn't do the full division, so it just kept the 10 value and printed that out. Okay. And then of course, this does appear again, but since it's overwritten, it doesn't look like anything changed. If we do divide by 0 multiple times, I don't have a clear screen within calculator or anything, but that just proves that the exception does work. The only issue is that I wanted it to be red. Oh, I'm doing color convert color. Yeah, I need to set the user graphics info to be that color. I don't need to do that. Foreground color equals that, and then what I'm gonna do, I'm not tired, who's tired? Is reset that here. There we go. Okay. That's what I wanted to do, was change the color because we saved it off. So setting that's not going to do anything. So we saved off the color. I'm changing it to red. We'll print a string that's red, and then we'll reset the color. That's all. That's a basic thing that I wanted to do there. So I'll just make sure I'm not crazy right quick. Not too much. And 3 times 2. 2 times 3, 2 times 2. Okay, 10 minus 1. 20 minus 490, negative 470. Okay. 1 divided by 0. There we go. Divide by 0 error. It's in red. It's scary. Exception handled. And then the program still moved on, so you can type stuff. Okay. Just wanted to make sure the exception does work. If we have additional exceptions, we can set them up now. In the exceptions file, so we can set up other interrupt handlers for exceptions with or without the error code. And then in the kernel, we can set those up, you know, down here after here. So there's one other thing regarding exceptions that I'm not going to change or fix. It's just, I want you to know it's broken if it is. And that was with rebooting. So before we could reboot and, you know, set a different video mode and come back. But I think now that we set up exceptions, jumping to the reset vector and everything's not going to work anymore. Yeah, we have a default exception handler and we got an error code. I don't know what exception number it is, so I should somehow get code to do that. But we do at least get an error code here, FFFC. And maybe I can do research on that and see if there's a way around this, or to actually do a more legit reboot sequence, you know, more to spec of how x86 works. But reboot does not work anymore after we set up exceptions. Just wanted to let you know. But at least we know what error code it gets. That's better than nothing, right? I can set up the PIC and hardware interrupts, even though we're not really going to use them. Or I can set up system calls. So I think system calls may be a little bit more pertinent to people. Maybe they're more excited about that. So I think I'll probably do that next. But then after that, I'll set up the PIC. All right, so continuing with system calls here. Before I get to that, I just had a couple tests because I was wondering how the sizeof thing actually worked in C, because I didn't really know. I didn't study that before. I didn't get to it yet in my books. So sizeof is a unary operator, so it will work like dereferencing a pointer, taking the address, doing a negative number. Those are all one, unary operator for an operand. Sizeof works the same way, except you can take the size of an expression that the unary operator would apply to, or you can get the size of a type. So at any rate, I made a small test program to test things for getting the address of an array element and also getting the size of the thing, because I figured that would look better instead of doing the 8 times 256 and then getting the address of the first element, make it look slightly cleaner. So this is just a small test for that. That has nothing to do with anything else. I was just, wanted to know. We have an 8-byte struct here and a 256 element array of an 8-byte struct. Then the size of that array and the size of 8 times 256, if it's defined as packed, no alignment issues or padding or anything, then they are the same size. The reason I'm casting it to a uint16 is because sizeof returns an unsigned long. So to only cast that, get the lower 16 bits, I put that cast there. Although I'm not exactly sure I need to do that. Maybe it'll be truncated to fit within the limit, I'm not sure, but doing that anyway. And then for the address, if you just take the address of an array, it is the same as the address of the first element of that array. But if you don't cast it, in this case to a uint32, then it would be the same as that array's type. So I could get just the address of the array, which is equal to the address of the element, but it would be the type of the array, which is, in this case, 256 elements of 8 bytes. That's the type of the array. So if I want to cast that just to a 32-bit address type, we can cast it to uint32. That's what I'm doing here. But that is equivalent to the single element there. And then the size of, we can use that to get the size of the sort of expression of this full interrupt descriptor table. If we wanted the type to get the size of the single type of that, it would be size of parentheses the IDT entry 32T here. So not that people need to know how sizeof works, it's just I didn't know. So if you're getting the size of a type, then you would put it in parentheses, otherwise you get a compiler error. Well, maybe not, but if you want the size of something, I guess, derived of that type, for lack of a better word, an instance of that type somewhere, then you don't need the parentheses. So you could just do IDT32, and that would be, in this case, 8 bytes times 256, which is 2048 or 4 sectors. But anyway, I'm just doing that to make it slightly simpler here to set these two values, and everything works the same. Just wanted to go over that real quick. So system calls, what I actually want to go over. So syscalls.h, this will be basically a syscall handler / dispatcher and system call functions. That'll be in this file here. For this, in this video, I'm just going to do a little test function for a system call to ensure it works. And later on, I can do actual system calls for malloc or something, something more substantial. But in this video, just going to be small test functions that are going to print to the screen again. So I'm going to include the print function, print types. I'm going to have a certain number of syscalls here just for clarity and to make it easier for error handling, I guess. I'm going to have a maximum number that I'm going to start out with, which is just going to be two little test functions here. And I'll have a couple functions to test those. I'll have test syscall 1 and 2. So these will ultimately be, we'll just have them be void, and it'll be, I think OpenBSD prefixes with sys. I don't know my naming convention I'm going to go with, but right now I'll just do this. I'll prefix these with sys for system call, or I can do system call. That might be easier actually. System call test 1 and test 2, we'll say. Or if I want to do the first two in C, they're probably going to be 0 based, so I'll do test 0 and test 1. Let's do that instead, because 0 based indexing is fun. But I'm going to have a table of these system calls, and basically when a system call is initiated from userland, or in this case, in this OS, just any program that is loaded and ran from the initial kernel, the initial shell, sort of process, even though I don't have processing set up. The system call is just going to be a regular software interrupt. That is, some interrupt number that is called from program called from the kernel initially, or I guess user land if you want to think of it like that. But, Linux usually uses 80 in hex or 128. That's what I'm going to use for my system call number. In the interrupt descriptor table at entry 80 in hex or 128, I'm going to put in a function for system calls. And then if the user puts a number into EAX, we'll say, and they call that function through the use of software interrupts, so the int assembly instruction. So if they end up calling, int 80h, after they move some number into EAX, we'll say 1 or 0, it doesn't matter. Then they call some function we have down here. I'll just call it the syscall dispatcher right now, or I'll just call it that. It'll end up calling this function because we're going to put this in the interrupt descriptor table at this entry number. They'll end up calling this, we'll interrogate EAX, and whatever function it is, we need to call whatever syscall that corresponds to. So syscall test 0 will be EAX0, test 1 will be EAX1, and so on. So how does that actually work? How would we call these? Well, I'm going to have a table, basically a table of function addresses that call these here. So I think I have to have these defined first to be able to do that. So I'll define those first, and then I'll have the sort of syscall table here, which is just going to be an array of function addresses. So I'm going to have them be void pointers, even though I could probably set them to 32-bit because I'm in 32-bit OS. They could be 64-bit later, so for less things I have to change later, I guess I'll make them void pointers. We'll just see. We'll do, I guess, syscalls, that's fine. And it will have entry number of max, system calls, we'll have it be compile time constant here, and it'll be syscall test 0, syscall test 1, so on and so forth. Though right now I only have these. But that's all it's going to be. It's going to be an array of function pointers, and these functions correspond to the system calls we want to run when EAX equals that number, and they call whatever software interrupt corresponds to this syscall dispatcher function that I'm going to lay out here. So for these two test system calls, I'm just going to have it right to the screen like the basic exceptions and interrupts. That's all I'm going to do right now. I'll put them lower on the screen though. So at like 20 and 21, we'll put the messages so we can see them on boot just for a test. And I'll change the color, like the divide by 0 is red, I'll make these like yellow and green or something so we can tell the difference. So first, let's save current text color, save the current text color, do that in both of these, and we'll print a string out after we set the new color. So I don't want to do that, I want to do user graphics info foreground color. For test 0, I'll make it yellow, why not? So RG, but no B. I think I have these defined in the graphics header anyway, but I'll just do this for practice. And I'll do test system call 0. We'll do that. Don't need to put a new line because it'll be reset for other things later anyway. And for system call test 1, I'll make it green. So no red, all green, no blue. And this will be 1. So it'll print down on the screen, you know, these two lines in yellow and green, just for testing later. I need the comma here, not there. Then what we have to do, so I don't forget, I need to restore the color as well. This will be color, restore text color. Okay, so the system call dispatcher is going to check what value is in EAX and call the appropriate function here by offsetting into this table. This is almost complete here, but what I'm going to do is write, since I kind of have to write these in this at least in assembly, because I don't want the compiler messing with anything, adding any extra code. I'm going to put an attribute on this, another one, a different one. This attribute naked, which means it's not wearing anything. No, it's The naked attribute means the function does not have a prologue or an epilogue, at least in Clang. Probably similar in GCC. I can't write anything in here other than assembly, well, inline assembly. So I'm assuming it works similarly in GCC, but yeah, there's no prologue function and epilogue. There's only inline assembly. So pretty much this is just a straight assembly function that you could use within C. It will only be what you put within this function body. But for my system called dispatcher, I'm going to go similarly to how the Dev Wiki handled system calls here. Yeah, Linux usually uses 80. I'll use 80 in hex for mine. You kind of have to do it in assembly so that the system call ABI doesn't mess up with other things, and so on and so forth. Linux gets its arguments that it passes in with a point regs structure. But I'm going to be doing like what they do, just push a bunch of stuff we might want to save, call the system call. I'm assuming this add ESP4 is for this, so I guess we're saving the value of the stack for some reason, maybe a local parameter or something that was stored there. Pop the rest of these that we pushed and add again to save EAX in case we want to see what that is on return if we had an error or something, although they're pushing an error, which I'm not going to do. But then also, since this is an interrupt, a software interrupt that we're using for the system call handler dispatcher, we need iret instead of the regular RET. And iret just means like an interrupt return from an interrupt. This D is for double. iret D would be for 32-bit because it's a double word. If you're in 64-bit, this would be iret Q for quad, depending on, your assembler mnemonics. But I'm going to be doing it like this. As far as when we do the call, I'll just be offsetting into a table like this. So instead of doing a jump, I'm going to do a call instruction, but I'm going to call offsetting into our syscalls array with EAX times 4. 4 because I'm in 32-bit. 64-bit, I'm assuming you do RAX or something times whatever you need to. But EAX times 4 because the number of the syscall you want to do is going to be in EAX. So if they call, and they want to do the first system call, they move the 1 into EAX. Since for me in 32-bit mode, all these addresses are going to be 32 bits. Technically, each one of these will be 4 bytes. So this 1 will be offset, 1 into this table. It'll be 4 bytes after 0. EAX is 1. 1 times 4 is 4. So you can just offset by the value in EAX times 4. That'll give you the right offset into this table here. So that's why we're going to be doing that. So I'll put basic syscall handler. Push everything we want to save. Call the syscall by offsetting into syscalls table with value in EAX and pop everything back and return using iReturn d/q, not regular return, as this is technically an interrupt. Well, it's a software interrupt. Okay. So when this is called, since it is an interrupt, there will already be values on the stack according to, the Intel manual I went over a little bit earlier. So we'll have the stack segment, the stack pointer, the flags register. In this case, it'll be E flags. And these will be, ESP and stuff. But anyway, stack segment, stack pointer, flags register. Code segment and the instruction pointer. We won't have an error code because it isn't an exception, just a regular interrupt here. So what we need to push is the things that aren't pushed as part of these. So all the other registers here, but already on stack, these we need to push, but AX, GS, we don't need to push all these, but I'm just copying what OSDev Wiki had. FS, ES, DS. BP, DI, SI, DX, CX. I'm not sure why they did it in this order either, but I'll just follow it. Why not? We'll do those. I'm just going to put an extra thing. Note here, easier to do call and Intel syntax, because I'm not sure how to do it. in AT&T. So I'm doing Intel syntax for this, which you can do within Clang or GCC inline assembly with the .Intel syntax. And I don't like prefixes because they're annoying, so Intel syntax, no prefix here. And then I'll just push all these things that we need to push here, which will be EAX and other stuff. GS, FS, we'll do this a little bit faster. DS, DS, BP, DI, SI, DX, CX, BX, okay. This will be EBP, EDI, ESI, EDX, ECX, EBX. Okay, and then I'm going to push the stack pointer again, even though it's already pushed. This is just how the osdev wiki had it. I'm assuming for local variables you might have within your system call handlers or your system call functions. Maybe you handle stuff on the stack locally. I'm assuming that's why they do this. I'm not exactly sure. But there's an extra push ESP there, and then the actual call. So the call I'm going to offset within this table according to the number they have in EAX. So system calls plus EAX times 4. That works. And that's how that actually works. If they have a 1 in EAX, it'll be 1 times 4, which is 4, which will offset 1, which is 4 bytes after this, and it'll call that function. That's basically how it works. Then after that, osdev wiki had add ESP4, I'm assuming again to save some kind of local stack variable, I'm not exactly sure, but then after that they popped pretty much everything back out. So the same thing in reverse order. BX, CXD, SI, DI, BP, DS, ES, FS, GS. Then at the top, I'm going to add ESP4 again. I'll save EAX by just adding to the 4 there. So this is B, this will be C, BD, this will be SI, DI, BP, DS, ES, FS, and GS. Okay. Then after we've pushed everything, called it, and popped it back out, I'll do the actual return instruction here. I ret D because we're double words, we're in 32-bit mode. I return because we're returning from an interrupt. Need interrupt return here. I ret, not ret. Putting that twice so I remember, just in case I'm confused later, which I might be. Okay, so the only other thing I'm going to add here is a little bit of, maybe not error handling. That's kind of the wrong way to say it, but in case they call us with a number that we haven't specified, so we have a max syscalls of 2. So what do I want to happen if they call with a number bigger than 2? Well, I don't really want to handle that because it's not handled so far, so I'm just going to return and continue without setting an error or anything right now, just to be basic and simple. So the way to do that here, in Intel syntax and inline assembly and Clang, or GCC, I guess, I'm going to see if I don't know if I have to do this exactly, but I don't think I could have the same define in inline assembly, so that's why I have to define it again here, because that didn't work when I was testing, for whatever reason. Have to define again. Inline assembly does not see the define. At least when I was testing, I couldn't get it to work, so I'm just defining that again here. And then we'll compare EAX to that number, -1, since we have 2, but we only go up from 0. It's 0 based, right? In the actual array here, the functions are 0 based. So EAX can be 0 or 1 to correspond to which one they want to call. EAX can't be 2, which would be the syscall number, because that doesn't exist. So we have to do -1 for 0 based. Unfortunately, syscalls table is 0 based. Okay. So if it's greater than that number, if it's greater than 1 in this case, and I think if it's 0, it'll be a bunch of Fs, it'll be unsigned, so it would be greater, hopefully. Let's do unsigned comparison instead, which is above. So jump if above. To some label I'm going to set up called invalid syscall, which I'll have just down here. But yeah, we'll just do that. Invalid syscall number. I guess I'll say skip and return, I guess. We won't do processing. So at the bottom here, I'll have a label, which is invalid syscall. And that's just going to do an iReturn like the other one. And then maybe so the compiler isn't messed up, not that it would be, I'll turn it back to AT&T with the prefix. Because I don't have the no prefix on there. Okay, and that will conclude the inline assembly block I'm doing. So that is the whole syscall system here that I have set up. Just see if we have a valid number, we're going to push everything, pop it back out. We'll call the syscall in the middle by offsetting into the table according to the value in EAX, which will call one of these function addresses, which will be the system call function. If EAX is 0 and you do int 80 after I set that up, it'll print test syscall 0, otherwise 1, print syscall 1. If we put EAX 2 or above, then nothing will happen. Hopefully. But I'll put that in the kernel and we'll see what happens. Call that syscalls, right? Yes, okay. Include interrupt syscalls. So let's see if that compiles. I didn't make any mistakes, and I did. Can't create dynamic relocation for whatever reason. The syscall table is in a read-only segment. Okay. So I did see something like this before, and I got around it by doing the z no text as a compiler flag, because I don't know how to write this differently right now. I didn't want to mess with it, but that's okay. I can do that. I think that's with the linker. Yeah, LD error. So in the make file where I'm doing linking here are the linker flags, which I don't have up here. Maybe I should add a linker flags make variable. -00 format binary. I'll do it after this. Dash z no text. Right? That's what it said. So let's see if that works. It does. Of course, the kernel rose in size. That's okay. Well, I guess first I could check that it works, even though I'm not calling it within the kernel yet. I want to check if everything else still works and that no text didn't mess anything up. Guess just to be safe, I can do that. So the kernel is 1F now. 2A, 3.7, 4, 5D. Can I press escape? There we go. Okay, 1E, 1F. All right. Do 768. So stuff still seems to be working well. Make sure the exception still works. That's good. Make sure I can still make a file. And we're all good. Okay. Just making sure. If I want to, I can rename that. Test F. And we have test F, and I can delete it. Oh, that deleted test font instead. So that's kind of a bug. So delete has a bug that I found out. That's good. But anyway, we can put this stuff in the kernel to test system calls and worry about that later. And I will do that down before here. So set system call handler. And that will be the same as setting a descriptor, except instead of descriptor 0, it's going to be 80 in hex or 0x80. Because when we call int80h, if we call int80h, or here in C 0x80, you know, that's the number corresponding to this interrupt, which is going to be in the interrupt descriptor table. So that's why I'm setting that there. And it was called syscall dispatcher, I believe. Yeah, syscall dispatcher. Okay. And then this will be instead, we're going to use an interrupt gate, but ultimately I'm going to be calling syscalls from, I guess, user functions, for lack of a better word. The privilege level will be 3 for the user level. And that was defined in IDT as int-gate user flags. I'll put that here. There we go. So int-gate user flags is what will be passed, so we can call this function from user level, user privilege level. That'll be at 128 within the descriptor table, so we can call int 0x80 and have that work. Okay. Actually, I'll put this over here. System call handler dispatcher. And this section will be set up. Software interrupts. Set up additional interrupts here, ... Okay, we only have one software interrupt here. It's valid so far. The other ones will be the defaults set up within init up here, init idt.32. Okay, so now that we have that set up, we can test calling the system calls. So I'll do that. I'll do debugging, testing, system calls. I'll leave these here, but I'll say uncomment these lines to test, I guess. We'll do that. So I'll have a couple assembly lines here. Yeah, it's an AT&T syntax, so I have to do move long, and constant will do 0 into EAX, and then I'll call int 80. So that should print test system call 0 in yellow, and then if we move 1 and call it, it should print test system call 1 in green below that yellow line here. And then if we move a 2 right now, this should do nothing. That shouldn't do anything because 2 isn't in the system call list. We only have 0 and 1 specified. So if EAX is 2, it should go to the regular I return from that jump we did. That should do nothing. But these should print lines on the screen. So I'll see if that works. Except it won't. Invalid operand int 80. Yes, because I don't know AT&T syntax. The 80 is a constant. Like these, 0 and 1 needs $1, the int 0x80 also needs $1. Okay, enter. I'll just take the default. Oh, we got system call 1, so I think I have these as the same y value, and that is why that didn't show the other one. But we know that it works because it did print that on the screen. And it went back to the kernel, to the shell, and we could type again. That's good. So I'll fix that right quick. This is y20. Yeah, I'll make this one 21. So we have both lines show up on the screen. Make that cursor y value 21 there for system call test 1. So there we go. Test system call 0, test system call 1 in yellow and green. So those system call functions were called, move 0 or 1 into EAX. We called the dispatcher with the int 0x80 because we put that into 0x80 offset into the interrupt descriptor table. So that was called when the int instruction was executed. It said, okay, EAX is 0. So we offset EAX times 4, which is 0, into the system call table to get the function address to call, which we then called, and it printed this line. Same thing for syscall 1. EAX times 1 was 4 bytes. Offset into the syscall table, which is the function address that was called, that then printed this line. So hopefully that makes sense. It's really not that hard, just setting up a table of addresses and then calling the addresses. But that's all I'm going to do for system calls in this video. We can set up actual calls later at whatever offset into that table we want. Like if we make malloc as system call 4, then we would just insert 4 to EAX and call, int 80. We'll probably put other values in to other registers just so they're preserved and we can pass them around. So maybe bx, if we did like a malloc function later, bx or dx or something could be the size in bytes that we want to allocate. And then we could say, or the size in sectors or something. And then if we call right now the physical memory manager, maybe I'll have a virtual one in a bit. We'll call whatever memory manager function we have with that number, and it will allocate that chunk of memory. It'll return a pointer, and we can return that pointer in EAX or something, since that was saved within the system called dispatcher. EAX was, and ESP, but since we kept EAX here, I could change this to return something, I guess, or we can just interrogate EAX on return from this, and maybe that would be an error code or whatever the return value of our allocate function was or something. We can set it up in some way and put it behind like a C function wrapper. So we're not doing everything within assembly if you don't want to. But that'll be later on. But system calls, pretty simple. That's all I'm doing here. Pretty simple stuff. But yeah, so the only other thing I wanted to do today was go over setting up hardware interrupt support through the programmable interrupt controller, or PIC. Although I'm not going to do any actual hardware interrupts for keyboard or anything, I just want to set up so that they work, right? Similar to these system calls and exceptions and things. So I'll get to that next. All right, let's get to doing some hardware interrupt setup here with the PIC, programmable interrupt controller, or PIC, specifically the 8259 Intel chip. For this, modern systems have the APIC and the io.h for advanced programmable interrupt controller, I believe. I'm not going to be messing with those, at least for now. I'll do it later when I learn how it works. But we'll stick with the simple one for today, 8259. And it sends, hardware interrupts to the CPU to take care of it. So if we set these up, we can put in sort of interrupt handlers for the hardware interrupts, so we don't have to pull the data port for the keyboard. We can just have the keyboard send an interrupt when it's ready, and then the interrupt handler for that keyboard hardware interrupt will do something with the key. We don't have to stick pulling data ports and everything until stuff's ready. It'll tell us when it's ready, and we can do processing and save time and CPU resources later. So originally in real mode and everything, the PIC was mapped to the first 16 interrupts in the interrupt descriptor, or the interrupt vector table in real mode, but in 32-bit, the interrupt descriptor table, the first 32 exceptions or interrupts are reserved by Intel for specific things. So if we leave the PIC how it is, still mapped from 0 to 15 or 0 to F in hex, it won't be easy to know if stuff went from the PIC or it was from a hardware exception or something, right? So we want to remap the PIC to a higher interrupt number than 0 to 15. Since the first 32 or 0 to 31 are mapped and reserved, we can set it to 32 to, 15 after 32, right? So that'll be fine. We can remap those, and there's ways to do that. And there's also commands you could send to the PIC ports here, 20 and 21 for the PIC 1, and A0 and A1 for the second one. We can send commands to the command port and read or do what have you with the data port. And we can remap the PIC to higher interrupt numbers so they don't interfere with the exceptions. And we can also mask or clear specific interrupts that we want to be able to service or not. So if we don't have a keyboard interrupt actually in play yet, we don't have a handler for it, we'll say, then we can mask that interrupt and it won't be fired off. Or we can clear it and then it will be fired off. Stuff like that. And there's other commands and things you can do, but that's kind of all I'm going to be doing today is remapping the PIC. We'll have a send interrupt thing because later on we'll want to do that. And we'll initialize it. We'll have something for disabling and masking. So that's all I'm going to do today. But okay, so I'll lay out these things in memory here. These command and data ports for the master and slave PIC. I'll do that. I just wrote this here, programmable interrupt controller functions. So I'll have a couple defines. I'll call it pic1 command and data. So pic1 is at hex 20. Data is at 21. And 2 is at A0 and A1. I'll just do that. That's an easier way. Getting my keyboard wrong. So, okay. That's the pic1, command port, data port. Pic2, command and data port. That's fine. The interrupts that I'm going to remap the PIC to use are going to be 32 and above. So I'm going to put that here as well. I'll call it new, actually. We'll do new IRQ. So the interrupts that the programmable interrupt controller controls are called interrupt requests, which makes things, more confusing. So, or IRQs for short. So these interrupts are interrupt requests. You also have interrupt service routines and, other things. But these are IRQs for specifically hardware interrupts by these interrupt controllers. So the new base for interrupt 0, I'm going to call it new IRQ 0. And it's going to start at 32 or 20 in hex. IRQ 0 to 7 will be mapped to interrupts 20 to 27. And then the same thing for the second PIC, the slave one. Instead of starting at a base of 8, it'll start at a base of 28, or 32 plus 8, which is 40. I'll do 8 to F, or 8 to 15. This will be mapped to 28 to, what is it, 3 or 2f? Yeah, 28 to 2f. Should be 40 to 47. That's what, 32 plus 15, that's 47, yeah, okay. So I'm gonna put in a small couple functions here. So I did that. I'll put in this, the EOI, I'll put in this code here and send end interrupt. That'll be fine, which just sends a 20 to the command ports here. And if you specified an interrupt request from 8 to 15, you know, that specifies the second pick. So we send it to there. Otherwise, we do 0 to 7, we send it to the first one. So they are also using, you know, some good abstractions here to see for sending in and output bytes using the in and out assembly instructions or machine code for x86. So I'm going to have some abstractions like that as well that I'll do right quick as an aside to this. So I'll actually have another folder, which I don't have right now. It'd be easier if I did just 2 levels here so I can see. So yeah, I don't have one yet. So I'm going to make yet another folder here and call it ports. And we'll do io.h. So Vim I don't have. Let me make that first. Little IO function header here. C abstractions for assembly in out instructions. We'll call it that. Make things a little bit easier. But this will be a pretty small file. I'll just have mainly, I think 3 functions here. So write AL to port DX. I can have separate functions for word, byte, whatever, or I can have one function and then make it a little confusing, I guess, but I'll just have it be one right now. Separate it out or do something, name these differently later if needed. So I'm going to have an out B, an out byte. So write a byte from AL to a port specified at DX, because that's how the assembly out instruction works. We'll give it up to a word value here, a port number, and a value that we want to write to that port number. So I'll do val or value. So we're going to write out an immediate 8 byte, is what this is going to be. AL will be used if applicable. And I'm going to use a little different inline assembly stuff here that I'll write out in a second. But I'll use an in constraint for the port number in case we want to write just to an immediate byte. So it's a little bit less code, or it can be optimized a little more. So I'll include this. In constraint will be converted to immediate constant. Do otherwise, it'll be out DX and AL will be used. Okay. So what do I mean by that? An inline assembly here. I'll do an output byte 0 to 1. So the first, whatever parm I give it, output that to the second parm, whatever I give it here. So I'm not going to be doing any output, but for input, for %0, I'll have a value in AX, so the A register here, and we'll be putting the value. So I want to write the value to some other parameter, it'll be to DX. So ND, so the capital N constraint, in case it's an 8-bit value and it can be converted and optimized by the compiler, it will do so and just do out AL to a byte. Otherwise, we have the D constraint here, which says we'll be using DX, the D register. And that'll be the port that we give this function. So if this value could be a byte, we'll write AL to a byte. Otherwise, if it needs to be DX, it'll write AL to DX. And this A corresponds to 0. This D or N corresponds to 1. We'll be writing the value to the port. But it's just a little abstraction. We can call out B and C, and it'll look better than inline assembly everywhere. Okay, otherwise we can read in a value. We can read in a value instead of writing it. But read in value from port DX to AL, and we'll return AL in this one. So I'm going to return a value from this. It'll be in byte from a port. And we'll have a return value. So I'm going to do return or ret val or something. Do ret val. I should probably set that to something as well, maybe 0 to start off, or -1, or although uint can't be -1. So I'm not sure, maybe I don't need one, and it doesn't matter. I'll think about that later. Might need error handling later. So same as before, we'll use the capital N or the D. So we'll do NAL immediate 8. That will be used if applicable. Otherwise, NAL DX will be used. Okay. We'll do n byte to the second parm given the first parm. Although we could do it similar to this one if we wanted. We just have to reverse order of things over here because, you know, AT&T syntax and everything. As an output, I need to overwrite the accumulator, overwrite so we can return the value. And we'll put that into the return value variable we have set up. So it'll overwrite AX with, you know, the value in DX or an immediate byte, and it'll return that. And then as input to this, I'll set in, you know, the immediate byte or the DX register here for the port number that was passed. Okay, at the end we'll return the return value, because that will be overwritten from AX here. We'll have an in and out byte function. We'll also have a wait function, io.wait. It waits approximately one IO cycle for IO operations to complete. So I'm going to need this within the programmable interrupt controller functions. So that's why I'm putting it here, because the osdev wiki page had io.wait, and I was like, what is that? And it's like, okay, there's a function you can do for that. Just call wait so it can wait between operations, which isn't really applicable in QEMU, but on actual hardware it might be more applicable. io.wait void. All this is going to do is read from a port, something that, assuming it's not going to be used for anything. So port 80, according to osdev wiki, is used for checkpoints during post, and the Linux kernel uses it. So Linux uses port 80 for stuff. So we're going to use it here because I'm assuming it works okay if they're using it. So we should be okay to use it also. So I'm going to do an out byte here. AL, so write AL to port 80. It doesn't matter what AL is, I'm just going to write it to port 80 here to take up one IO operation, approximately. No in, no output. The input I'm going to put into AL some value. I'm going to put 0. I'm not sure if I have to set AL, but we can be sure that it's set just in case. So we'll write a 0 byte to port 80 for no reason, then we can. And if it turns out that's used for something important later, then I can change this then. But this is what osdev wiki had. I'm just kind of copying what they had, you know. Just a couple small functions here to abstract IO ops. But okay, that's all I'm going to do for that. I'll just make sure things compile first by putting it down here. Ports, IO header, put that in the kernel. So I didn't mess anything up there, that's good, okay. So I'll go back to the pic file. And I'll put in their thing that they had, the send end of interrupt here. That's hex 20, takes in a character. Define pic, end of interrupt. We'll do 20, end of interrupt. So I'll have that here. Send end of interrupt command to signal. IRQ has been handled. Otherwise, if you have an IRQ function and you don't send the end of interrupt, what this does is signal to the pic that we're good to go on. So if you don't send this, then the pic will still be waiting and you won't get any other interrupts sent unless you send this and handle it completely, right? This signals you're done. You can move on to the next interrupt or back to normal processing, right? So if you don't send this at the end of your IRQ functions, then you'll service the first one, but nothing else will happen. So you kind of want to send that. And I'll do this, send pic EOI, we'll pass it whatever interrupt we're handling here. So I'll do uint interrupt request. So if we're at 8 or more, we want to send it to the second pic. So we'll write an output byte here to pic2. Pic2 command. The interrupts, the programmable interrupt controller, the pic1 and 2 are kind of set up together. So the interrupts are sort of cascaded. Interrupt or pic2 is set up actually as the second interrupt in pic1. Well, we'll do that later, but so what that means is we send this to pic2 and then we send it to pic1 to say, hey, we handled the interrupt. But we send this first to pic2 so that it doesn't try to, rehandle it from the first pic after we're done, pretty much. But what value are we sending to the command port for pic2? We're sending the end of interrupt value. But regardless, no matter what, we have to send that same value to the pic1 port to say, hey, we're done servicing the interrupt. It's just if it goes to the second pic, it kind of sort of goes through the first pic into the second pic because they're kind of wired together in practice. It's not exactly right, or it is, but I don't say it right. But anyway, we have to send it to both if it goes to the second one. That's all I want to say. So we have an end of interrupt function. So there's also initialization that you do for the pic, but I'm going to set up a disable function first because that's small. We can do here as well. If we want to disable the pic and not service any hardware interrupts through it, maybe we have an APIC or something we want to set up later, or we just don't want to handle hardware interrupts. We can do that here. So I'll just call it disable pic. And all we do for that is to the command ports again, we write out bytes, but we just write FFs. So we did this we send it to the data ports actually. So I'll send it to the second one first, and I'll send 0xFF. So that is the sort of, I guess, disable command. So I could make that a non-magic number as well. This just disables pic. You want to do this if you're using the APIC or io.h, or I guess other ways of handling things, but this disables the normal pic. It will not disable the advanced ones. But you'll want to do this if you're using these so that you don't have redundant things or errors from trying to use the regular one when the advanced one is what you're actually using, so on and so forth. So this just disables the regular pic1 and 2 here. Maybe what that effectively does is mask off all the interrupts so that they don't fire. That could be what it actually does, and that would make sense, but I don't know. That's all we're going to do for that. You can also mask off specific interrupts you want to do by messing with their interrupt mask register values. So if an interrupt is fired and that it's set sort of in the interrupt mask register, if that bit for that interrupt is set, then that means we don't want that interrupt to be serviced, so it's not going to do anything. So we have a couple functions for setting and clearing that bit mask in there. If the mask is clear, if the bit is 0, that interrupt can be serviced and it'll go on to be handled by whatever function you have for that interrupt request. But if it's set, it won't be handled. So I'll have a couple functions for that as well. So set IRQ mask, I guess, by setting the bit in the IMR, interrupt mask, register. This will ignore the IRQ. I'll do sets IRQ mask, giving it some IRQ number. And we'll have a port and a value, I guess, because that's what I did. Yeah, okay. But we'll be sending some values to some ports here. That's why I have those variables. If the interrupt request number that we want to set is less than 8, then we send to the first pic. If it's greater than 8, we send to the second pic. So it's less than 8. My port's going to be for the first one, and these values will be sent to the data ports for their respective pics. I'll do else. We're going to subtract 8 from the number. So if we send 8 to 15, we're still going to be sending 0 to 7, but it'll be to the second pic. So we still want to send the number 0 to 7, but we can overall set the mask for interrupt 15, right? That'll be interrupt 7 within the second pic. So interrupt 8 would actually be interrupt 0 in the second pic because they're 0 based. And then port will equal the second pic, so it'll be pic2 data. So how I'm going to do this is get the current interrupt mask register value set on the IRQ bit to mask it, then write new value to the IMR. And I also had this as a note. If you mask interrupt request 0, according to how I set it up and how it's usually set up, the second pic is on interrupt request line 2. So if you mask the second interrupt request to prevent interrupts from firing, that will effectively disable the second pic from firing, interrupts 8 to 15, since it's on the first interrupt, line 2, and pic 1. So just that's what I'm putting as a note here. Or raising, I think that's what it was called, raising IRQs due to second pic being mapped to IRQ 0 and pic 1. Which I'm going to do that later, but that'll just be applicable here. So the value I'm going to read in the byte in whatever port we're doing. So I'm going to read in the pic 1 or 2 data port value, which will effectively be the IMR value. I'm going to OR that with 1 shifted left by our request number. So that will set that 1 bit within this value, and I'm going to write that value back out. Write it back out to the port. So I'll take in the current value of what is masked and what is not. I'm going to set that additional mask here, and that interrupt will no longer fire because we'll write it back out to the port. So that makes sense that if you're writing FF to the data port, that would mean that all of the interrupts are masked, so none of them will fire off or be raised. So that's why this disable works. That makes sense. It actually writes to the IMR and masks them all off. That makes sense. If we have something to set a mask and enable interrupts, we'll probably also want something to clear a mask and enable interrupts. So we'll also have that. I'll have that here. This will be, well, clear interrupt request mask by clearing the bit. This will enable the IRQ or enable recognizing or whatever. I don't know. I put recognizing in my notes, so I'll do that. This will be clear IRQ mask, and these will be the same. We'll get the current value. Instead of setting the bit, we'll clear the bit to unmask it and then write the new value. And similar note here, clearing IRQ2 will enable the pic. Will enable the second pic to raise IRQs due to it being mapped to IRQ0 and pic 1, which I'll do after this. So we want to read that value in. And instead of setting it by ORing it with 1, I'm going to clear it by ANDing it with 0 or not 1 here. That's, you know, the basic way to clear the bit there. And then we'll write that back out. So we'll have functions to clear a bit mask, set the bit mask for enabling or clearing interrupts, disable all of the interrupts, and send an end of interrupt later on. Okay, so the last thing to do here is to actually remap the pic so that it uses these other interrupts instead of 0 to 15. We want to remap it to at least 32, which I'll do. Okay, so I'll have a function to do that here. I'll have a remap pic function. It'll just be void, remap pic void. Put it up on the screen a little bit. Okay, so how do we go through and remap the pic here? I'm gonna have a couple character byte variables here. I'll have a mask for the pic 1 and 2. And that is it. So I'm going to save the current masks by reading in the bytes. So in byte from pic 1 data and 2. Okay, I'm going to try to finish this up tonight with the pic. Saving off the current mask for this, the current interrupts that are activated, disactivated, so that I can restore them later, which I'll put down here. Put some comments here I'll go over because we put these in the mask. So what I'm going to do to restore these masks is just write the data back to the data registers here. So that'll be an out byte into 1 and 2, the 1 and 2 data regs for the 1 and 2 masks. Just do that. Pick 2 data, pick 2 masks. Okay, because we're going to be messing with these, so messing with that register, so we're just restoring and, yeah, saving and restoring. So to actually remap the pic like I want to do, we need to send some bytes to the command or the data registers for both, and they're called initialization control words, or ICWs. So this is a better tutorial I found that goes more in depth over these, but basically to remap the pics to use different interrupt addresses and everything, we need to send these initialization control words, or ICWs. The first one sets up whether you're going to send more than one, pretty much. So you can send from 1 to 4, and I'm going to send all 4, just, you know, to get everything set up right. So the first byte that we send to the command register, so 20 or A0, pick 1 and 2, we're going to send ICW1. I am going to set bit 1, and I am going to set this bit. So we're going to initialize the pic by setting bit 4 and bit 0, just to say we're going to send up to 4 ICWs for this. I'm not going to set these 3, 5, 6, 7, because they have to be 0. Bit 1 you would set if there's only 1 pic. We're using at least 2, so this will be cleared. So bit 0 is set, 1 is cleared. x86 defaults this to 0 usually, we're doing that. And I'm going to operate in edge triggered. Otherwise, if it's level triggered, when it's activated, it'll keep being set till it goes back down to a rising or falling edge, I guess. But we'll do it edge triggered, so it's only activated once on the rising or falling edge whenever it happens. For my very limited electronics knowledge there. Yeah, we're an edge trigger by default, leave it at 0. So I'm going to send 1, 1, so that only bit 0 and 4 are set to initialize the pic and also to receive up to 4 ICW words. And I'll send that to both of the interrupt controllers here. So I'll send that to both, and we put that to the control or the command registers. So I called it command, right? And not data. Not Star Trek, okay. So command will send 1, and we'll send that also to number 2, just to tell it both we're initializing the thing. So this will be ICW1, bit 0 equals send up to ICW4, bit 4 is initialize the pic, okay. So then we'll send ICW2, 3, and 4. So what are 2, 3, and 4? ICW2 says which interrupts we're going to use with the pics. So the base address of the interrupt vector, the interrupt descriptor that you're going to use. So they're normally mapped to 0 to 16, but since those are reserved for exceptions, we don't want to overwrite those and be confused. We can set these higher to at least 32. So I'm going to set, you know, pic 1 to 32. So I'll just send those values here. I'll send 20 to the primary pic 1, to the data port that says, hey, you're going to be handling interrupts now starting at, you know, offset 20 hex into the interrupt descriptor table. And then pic 2 I'm going to set to 28 or 27 in hex, whatever it is, to its data port to say, hey, you're handling, you know, these next 8 interrupts starting at that offset into the descriptor table. So I think I have these defined up here as new IRQ 0. Yeah, this should be IRQ 8 I'll do. So yeah, 0 to 7 and then 8 to 15. So this one I'll send to pic 1, this one I'll send to pic 2. You could reverse and be really weird, but don't do that. We'll just send this to 1 and this to 2 in the data ports. The only ICW that needs to go to the command port is ICW1, effectively to say we're initializing, sending the initialize command, and then we send the data for the other control words to set up how it's going to work. I think that's how I understand it. So these ones will be going to the data ports instead. And we'll be sending new IRQ 0 and new IRQ 8. Okay, so pic 1 will then be mapped to interrupts 32 to 39, and then pic 2 will be 40 to 47. So those will be the hardware interrupt descriptors in the interrupt descriptor table that we can then make functions to set up and handle these pic manage hardware interrupts later on. So interrupt control word, or in initialization control word 3 will specify where the cascading pic, where the second pic is set up from the first one. So x86 defaults to using the second interrupt, IR2. So interrupt request 2 offset from 0 to pic 1 would go to the second pic. So if it's remapped to hex 20, it would be hex 22 would be going to the second pic now, but ICW3 sets that up. But it's a little confusing because the word you send to the primary pic, is the bit number corresponding to the IRQ line. So it would be binary 4 or bit number 2, 0 based. But the one you send to the secondary pic, the number is in binary. So you send a binary 2 instead of a binary 4 to the second pic. So it's a little confusing. You send the bit number of what IRQ you want to go to the second one to the first pic, and then the second pic you set its IRQ number from the first one, but in binary. So that's a worse way of saying it, but you send a 4. If you want it to go to number 2, send a binary 4 to the first and a 2 to the second, like they're doing here. So I will do that. 0x4 and 0x2. Where to map the base interrupt, the IDT. CW3 is where to map pic2 to the IRQ line and pic 1. I guess that's the way of doing it. Mapping pic2 IRQ 2. Bit number. Bit 2 equals IRQ. So yeah, the first one as bit number 0 based, 0100 is bit 2, 012 second bit, IRQ 2, and the second pic, binary number for IRQ, pic 1, 010 or 0010 for nibble, equals 2. Okay. And then between all these that I haven't been doing, but they did in the osdev wiki, in case you have a slow machine, these might take a while to take effect, even though I'm not using a sort of wait function in other areas, like in the disk reading and loading functions. Maybe I'll have to do that later for real hardware, I don't know. They had an IO wait in between these, so I'm going to do that as well. So when it sends it and it's setting up from sending stuff to the command register, yeah, I'll put an IO wait, which was defined in this ports header file, or IO header in the ports folder, to just read whatever, send a value to port 80, whatever, just to take up some IO cycles. So calling IO wait will do that, and that'll be fine. And we'll send that basically after every one of these. I'll put 2 there just in case, but that should be all I need to do there. So ICW4. Just to put some delays in just in case. ICW4, the last one we have to send, specifies whether the pic is working in 8086 mode or x86 mode instead of MCS 8086, because it was a general controller, it wasn't only for x86, but we'll be setting the first bit here to specify, yes, it's x86, and we won't really set any of the other ones. 5 to 7 have to be 0 anyway. I'm not going to use buffer masters and buffered mode because I don't know about it and I don't want to use it, and I'm lazy. Special fully nested we're not going to use. According to this guy, I think it wasn't even supported. x86 doesn't support that. So we'll set bit 4 off, 5 to 7 will be off. I'm not doing buffered mode, so these 2 will be off. And I'm not going to mess with automatic end of interrupt, although that sounds interesting. I'm not sure how it works in practice. So the only bit I'm going to set is the first one, so I'm just going to send a 1, binary 1, whatever, decimal hex 1, to both the data ports for ICW4. That's all I'm going to do for this. I'm going to do set x86 mode. I can type in 8. Pic 1 will send a 1. And to pic 2 we'll send a 1. And that's all we have to do there. Pic should be fully set up now, nothing more to do, because we sent the initialization control words, it's all initialized, so that's why I'm restoring the mask after. So whatever interrupts were enabled, disabled here, are going to be the same ones after we reinitialize it. What I'm going to do in the kernel is actually just disable all of them, and then we can re-enable them later selectively when we have functions to handle those interrupts. That's why I have these comments here, because I almost forgot what to do. It's been a few days. So put code to disable and remap the pic, and then add hardware ISRs and clear the mask to enable them, and then enable hardware interrupts. And that will be all we're doing today. So I will put that in right now. We have the kernel. So after software interrupts and we do the tests, I'm going to put them here. Can I move this over to the left? Well, I guess I can do this, right? Just do that. What was that? B1? Buffer 1. All right. Well, my head's probably in the way of these, so I'll put that up again. Do those comments there. Okay, so I'm going to basically mask off all hardware interrupts. Disable the pic. That's what that does. And that will be a call to disable pic, right? Yeah, just disable pic. All right, and then we'll remap it. Pic 1 starts at 20. Okay. And that will just be a call to remap pic. Remap pic. Okay, not too bad. Add hardware interrupt ISRs. So we'll do this later. I'll put to do items, of course. So add ISRs for pic, hardware interrupts. We'll do that here. That'll be, you know, setting up interrupt descriptor for things. A couple examples in my notes were the pic normal interrupts 0 and 1, which are now hex 20 and hex 21 because they've been remapped here. These aren't, you know, these aren't made, so they'll be commented out. But 20 and 21 all said, those might be the ones that I start with. 20 would be for the timer, I guess from the programmable interrupt timer maybe. But this will be timer IRQ handler, whatever I end up calling it later. And it won't be user necessarily, it'll just be interrupt flags. One thing I didn't explain, if we enable interrupts with STI without masking them all off, there will still be stuff running that's been running the whole time. We just haven't been accepting the interrupts because we did CLI to clear the flag back in the bootloader or wherever. But there's stuff still running like the programmable interrupt timer, the PIT. It'll be sending timer ticks every 18.2 seconds. Or sorry, that'd be very slow. 18.2 timer ticks per second. Stuff like that. And if we don't have a handler for it, well, we have exceptions set up, but those might not work anyway. If we don't have a special handler to handle that and send an end of interrupt request and things, it'll keep generating and either hang stuff up or make like a triple fault and reset, and that wouldn't be good. So until we handle the timer, I'm going to not enable that. Normal pic interrupt 1, IRQ1, in this case remap to 21 in hex, 32 or 33 will be, I think, for the keyboard. Yeah, this will be the keyboard IRQ handler. So later when we make that, we won't have to just keep reading the data port and the get key function that I have. We can actually just handle it in here in an interrupt and add to some new buffer for keys or something. And then when we go to get a key, like here, we can read from a buffer if it's not empty, stuff like that. We can press a key and just keep in a loop until we receive a key from our new keyboard buffer we make somewhere. When it's an enter key, go on. So we'll have to redo logic a little bit maybe, but it'll be better because we won't have to go and waste resources in a busy loop. We can actually handle it how it should be handled. But maybe if you're in a real-time OS or something, you'd still do it the old way, I don't know. But those will be later, and you know, put more here. Put more IRQ handlers here. Do pick IRQ to be pedantic. Okay, but if we have those later and we set them up, we want to clear after we add these and put them in the interrupt descriptor table to enable the interrupts later. We'll put that here. Enable interrupts. I'll do pic IRQ interrupts after setting their descriptors. Okay. And that would involve calling the clear IRQ mask function to clear that bit within the mask register, which is just the data register when we read it or write to it. So later when we make these, we can clear that bit within the pic registers, and that will enable the interrupt to be handled. So until that bit is clear, the interrupts won't be handled, so it doesn't matter. We could set the descriptors, but they won't actually work until we clear that bit that says, hey, you can send the interrupt now. So we'll do that later, such as for 0 and 1. Because the pics still work off 0 to 7 and 8 to 15, right? Well, 0 to 7, it's just if it's 8 to 15, we make it 0 to 7 to the second pic. Even though on our end, they're remapped starting at 32, the pic itself handles from 0 to 7, right? So we'll have to clear interrupt mask 0 will correspond to 20 since they're remapped. 1 will go 21, so on and so forth up to F or 15, if that makes more sense. So this will be enable timer. We'll tick every around 18.2 hertz, 18.2 times a second. These are just examples here. Enable keyboard interrupts. After we did all that, we can enable the interrupts with STI. So this should actually work. I mean, none of the interrupts are being handled since we masked them all off with this disable. But the system should run, at least in this emulated QEMU, it should run fine, should run exactly the same after we do this. It's just they're enabled now, so they're all masked off, so it won't do anything, but if they were, then they should be working. But I'll just test that and make sure if I didn't call them wrong. Ah, yeah, implicit. I have to add it down here. Do this. This is pic.h. Where's that at? Outbyte. Oh, I didn't put a semicolon, or that was in the other file. That was in this file, wasn't it? Yeah, I didn't put semicolons. That's what I get. That's what I get programming in lesser languages where I don't remember that. Okay. And then now this doesn't work. Invalid. That is in ports. It doesn't like it. That didn't work. I think I have to do 2 to put it out to a file. We'll do that. So standard error will go to test. So now I can run less on that. This is how I do errors sometimes to keep them all in a separate thing. Just redirect the output here. So pic doesn't like that. Implicit, because I don't know. Oh, okay, yeah. Since I have io specified after this, it doesn't see these definitions. So I could include io within pic, which is what I should do. Or I can put it up here. But I'll just include io within pic, that's fine. So it won't do anything since it's after it in the kernel. It won't re-include it, hopefully, but I do want things to be more, I don't know, agnostic or something. I want you to be able to move them around if you need to, so. Pragma once will do it up here, include, should be in here, interrupts, or no, it'd be port. Ports io.h, that's what it was, right? Hopefully. Yes, okay. There we go, now it compiles. So 1F, 1D, 0D, yes, that is right, okay. No more data was taken up. So 1024.768, we initialized, we got the test system calls, 2 didn't do anything. They should all be working, should be able to load and run everything. Exceptions will still work. Test file. We have that. Can make the font bigger. No, we can't. Did I call it with a big F? I did, okay. Control L doesn't work because this isn't Unix. CLS, okay. But everything still works now. Everything's still fine. So that's good. Even if it takes a little bit. Just make sure scrolling still works. It's good. Okay. So that's all I'm going to do in this video. The next one I might mess around, make a either a system call or an actual hardware interrupt for the timer or keyboard or other software interrupts. You know, we'll see. I probably won't do other software interrupts, but maybe an exception handler if I want, or something where the timer and keyboard are another hardware interrupt from the pic, or a system call or something. So that might be the next one. I may also start or do a virtual memory manager and paging. And then after that, do a system call for like a malloc type thing to allocate memory at runtime so that our editor can allocate memory and load a file, stuff like that for that progression. Or I might do something else. I don't know. So let me know what you want to see and I can look into it. But that's all I'm doing today because I'm tired. My voice is dying. And that's all I got. Hopefully you enjoyed. Hopefully you learned something we set up and we have working other than reboot. That's broken from exceptions now. Although at least we get the error code so we can look that up. I still need to do that. But we have working interrupt support now at a basic level. Software interrupts, exceptions, system calls, and hardware interrupts that are all masked off so they don't work right now because we need interrupt handlers for them. But it's all good. So yeah, that's all I'm going to do. Thank you for watching. I will see you on the next one.